So we found out that x1 is entering variable because as we look at the set of non-basic variables, which are x1, x2, and x3, and we look at if we increase any of these three in terms of increasing the decision variable, x1, x2, and x3, since x1 is multiplied by 60, it shows x1 causes the greatest rate of increase. So if x1 increases from its current value of 0, it will have to become a basic variable. So right now it's non-basic. We want to make it a basic variable. So for this reason, x1 is called the entering variable. Observe that x1 has the most negative coefficient in row 0. So if we go back to the table, this is what I'm referring to. So if you look at row 0, x1 has the most negative coefficient when compared to x2 and x3. So we know, so we chose the entering variable in a maximization problem to be the non-basic variable with the most negative coefficient in row 0. If there's a tie, we broke the tie arbitrarily. We decided to make x1 as large as possible, but as we do, the current basic variables s1, s2, s3, and s4 would change value. Thus, increasing x1 may cause a basic variable to become negative, and we don't want that. So from row 1, we see that s1 equals 48 minus 8x1. So since s1 has to be greater or equal to 0, the maximum value that x1 can have is 48 divided by 8, which is equal to 6. And that's obtained by solving for x1. In the same thing, we look at row 2, we see that s2 is going to be equal to 20 minus 4x1. Since we know s2 has to be greater or equal to 0 to be a basic variable, the maximum value to keep s2 greater or equal to 0 that x1 can assume is 20 divided by 4, which is equal to 5. Now from row 3, we see that s3 equals 8 minus 2x1. Since s3 is greater or equal to 0, x1 has to be less than or equal to 8 by 2, which is equal to 4. From row 4, we see that s4 is equal to 5. So for any x1, s4 will always be greater or equal to 0. So again, we want to keep x1, s2, s3, and x4 greater or equal to 0. Those are the basic variables. They need to be positive. But as we make x1 an entering variable, we have to choose one of these 4 to leave the set of basic variables. So in order to do that, we have to look at this, what we call ratios. And we're gonna find out which of these decision variables, basic variables, S1, S2, S3, and S4 will leave. So this means to keep all the basic variables non-negative, the largest we can make x1 is the minimum between 6, 5, and 4. And that minimum is going to be equal to 4. So using that information, this is what we call the ratio test, and I call it the minimum ratio test. When entering a variable into the basis, compute the ratio. The ratio is going to be equal to the right-hand side of the row divided by the coefficient entering the variable in that row, or the coefficient of the entering variable in the row. For every constraint in which the entering variable has a positive coefficient, the constraint with the smallest ratio is called the winner of the ratio test. The smallest ratio is the largest value of the entering variable that will keep all the current basic variables non-negative. Make the entering variable x1 a basic variable in row 3, since this row constraint was the winner of the ratio test. To make x1 a basic variable in row 3, we use the elementary row operations to make x1 have a coefficient of 1 in row 3 and a coefficient of 0 in all the other rows. This procedure is called pivoting on row 3. And row 3 is called the pivot row. The final result is that x1 replaces s3 as the basic variable for row 3. The term in the pivot row that involves the entering variable is called the pivot term. So this is what we are referring to. So here we have step 5. We're going to use the Gaussian method using the elementary row operations and simplex tableaus. We make x1 a basic variable on the next slide. So as you can see, this is the original table in which we have our non-basic variables are s1, s2, and s3, and s4. So we have chosen x1 to be our entering variable. And we have chosen, after performing the minimum ratio test, we have found that the minimum is in row 3. So, here we have, these are my basic variables. These are my basic variables, S1, S2, S3, and S4. Okay, so X1 is entering, right? We found that we don't have an optimal solution yet. So by looking at the most negative value here in row 0, we found out that minus 60 is the most negative value. So X1 is entering. And then we know that S3, based on the minimum ratio test, which we perform here, we look at these ratios, 6, 5, and 4. Row 3 gives us the minimum. So this guy is leaving. S3 is leaving. So S3 is leaving. So I need to find the intersection of both. So that intersection is this number right here. So if you observe on this side of the table, if I complete these zeros, we can identify the basic variables by looking at the format of their columns. See, that's the identity matrix. So the identity matrix is showing you who the basic variables are, right? And the non-basic variables, they don't have the format, right? So this is also zeros. This is zeros. Okay, and then Z, right? So S3 is leaving. So what that means is that this column right here has to become this column. So the format of that column has to be now 0, 0, 1, 0. And we are going to use the elementary row operations. We're going to use the elementary row operations to make a column equal this. Okay, so that's what we're going to see on the next slide. So our first step is to make this equal to 1. All right, so let's fill out the rest of this table. Okay, 0, 0, 0. I'm going to change this color to black. Okay, so we make this equal to 1 by multiplying by 1/2, right? So if we go back to this slide, this number is 2. So we want to make that equal to 1. So we multiply the row 3 by 1/2. Okay, so if we go back here, let me exit variables and make another column here to illustrate what's going on. So if you look at this line, Z, these are my basic variables, Z, S1, S2, S3, and S4. Now I'm making, this is Z, S1, S2, and now X1 is going to become a basic variable. So that's why I'm making this column a column with ones and zeros. So I'll make that equal to 1. Now, the next step is to make the rest of this column zeros, right? So I got the 1, now I need to make the rest of it equal to 0. So what we're doing next, I wanna make this minus 60 equal to 0. So the next step is to multiply 60 times row 3 and add that to row 0. And we have obtained that 0 here. Okay, so I need to work on the other 2 now. So let me also update. These are my basic variables. Again, just to keep everything. So this is X1, Z, S1, S2, and S4. So next step is to make this 0, right? So I'm multiplying row 3 by minus 8 and add that to row 1. So that's gonna make this 0. This was already 0. This was already 0. So I'm almost there. Still to make, I need to make that 4 equal to 0. So that's what I'm gonna do next. So I'm going to multiply minus 4 times row 3 and add it to row 2. And let me keep this here so you understand what we are doing. So this is X1, this is Z, S1, S2, and S4. So now I have this column in the format. I have completed the iteration. As you can see now, S3 no longer have that format for the identity matrix because it is no longer a basic variable. So my basic variables now at this point are S1, S2, X1, and S4. So if we put this into the canonical form, you go back here, you look at this table, this is row 0. So row 0 always represent the objective function. So let me use highlighter. So this is row 0 right here. Right? So if we look at this in the canonical form, this is what we have. Okay, so the objective function has increased from 0 to 240. And then the rest of the rows in the Tableau this row, this row, this row, and this row are represented here. At this point, these are our basic variables, and these are the values for our basic variables. So in canonical form 1, the basic variables z, s1, s2, x1, and s4, and non-basic variables s3, x2, and x3, yielding the basic feasible solution z equals 240, s1 equals 16, s2 equals 4, x1 equals 4, s4 equals 5, and s3, x2, and x3 equal to 0. The procedure from going to one basic feasible solution to a better adjacent basic feasible solution is called an iteration of the simplex algorithm. And that's what we just completed, the first iteration. So returning to step 3, we attempt to determine if the current basic feasible solution is optimal. Rearranging the row 0 from canonical form 1 and solving for yields. Solving for z yields this equation: 240 minus 15x2 plus 5x3 minus 30s3. The current basic feasible solution is not optimal because increasing x3 to 1 by holding the other non-basic variables to 0 will increase the value of z. Making either x2 or s3 basic will cause the value of z to decrease. Step 4, recall the rule for determining the entering variable in the row 0 coefficient with the greatest negative value. Since x3 is the only variable with a negative coefficient, x3 should be entering into the bases. Performing the ratio test using x3 as the entering variable yields the following result. So this is the minimum ratio test from row 1. S1 has to be greater or equal to 0 for all values of x3, since S1 is going to be equal to 16 plus x3. From row 2, S2 to be greater or equal to 0 only if x3 is greater than 4 divided by 0.5, which is equal to 8. And for row 3, x1 is going to be greater or equal to 0 if x3 is greater than 4 divided by 0.25, which is equal to 16. From row 4, S4 is going to be greater or equal to 0 for all values of x3, since S4 is equal to 5. This means to keep all the basic variables non-negative, the largest we can make x1 is the minimum between x8 and 16, which is equal to 8. So row 2 becomes the pivot row. Step 5, now we use the elementary row operations to make x3 a basic variable in row 2. So we go back to this iteration, right? So let me go back here. So we stop here. Remember, this is our last Tableau. This is our last Tableau. So we are copying that last Tableau into here. Okay. So looking at the format of this, we include those zeros. Okay, so this is 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so based on what we just discussed, we can look at row 0 and we can identify, let me say, these basic variables at this point are S1, S2, X1, and S4. So we can identify from row 0 what will be the largest negative coefficient in row 0. And that largest negative coefficient is going to be -5. So that means that X3 has to enter the basic variables. Okay, so X3 is going to enter. Now we have to determine who's going to leave, S1, S2, X1, or S4. So in order to determine who's going to leave, I had to perform the minimum ratio test, right? Which is performed by looking at the right-hand side, and we're going to divide the right-hand side by the coefficient of X3. Okay, so the first division is 16 divided by -1, which is a negative value, and we don't consider that for the minimum ratio test. Okay, so we continue with the other one. We have 8 divided by 1, which is 8 divided by 1, and that is equal to 8. Then we have 4 divided by 0.25. 4 divided by 0.25 is equal to 16. And then we have 5 divided by 0, which is undefined. So defined, so this doesn't apply. So we have the minimum between 8 and 16, which is equal to 8. So that means that S2 is leaving the basics variables. Okay, so now I'm going to write my basic variables again. So S2 is leaving. So this is S1. Now X3 is going to be in this position. X1 is going to be in this position. And S4 is going to stay in the same position. So let me fill out all this. Let me do this for the rows, for the rest of the problem. So these are zeros. Okay, so at this point, we know that X3 is going to enter and S2 is going to leave. So the first step is to let me check something quickly. Okay, so this is what I wanted to check. So this right here was 1/2. So at this point, what we are doing to make that equal to 1 is to multiply by 2. So that makes this equal to 1. And now the rest of the elementary row operations will make this equal to 0, this equal to 0, this equal to 0. Okay, so how do we make this equal to 0? How do we make -5 equal to 0? We're gonna add 5 times row 2 to row 0. And that's how we make this guy right here, -5 equal to 0. Okay. So now we need to make this guy and this guy right here equal to 0. So on the next iteration, I'm going to add rows 2 to row 1. So I'm going to add this guy to this guy, and that will make this equal to 0. So I have 2 zeros. Now this is what's left. So to make that equal to 0, I'm gonna add -1/4 times row 2 to row 3. And that's going to make this equal to 0. And now we have this column in the format that we needed to. Okay, so remember, these are my basic variables. Z, S1, X3, X1, S4, and my basic variables here, Z, S1, X3, X1, and S4. Okay, so at this point, we have gotten to this solution. Right now we have, if we look at the rows, the objective function Z equals 280. Okay, so this is my right-hand side. This is S1 equals 24. This one is saying that X3 equals 8. This one is saying that X1 equals 2. And this one is saying that S4 equals 5. So I have an objective function now is equal to 280. So it went up from 240 to 280. So this is the canonical form. One more time, we put this into the equation forms. And you see the basic variables are Z, S1, X3, X1, and S4, and the non-basic variables are S3, S2, and X2. Yielding the basic feasible solution Z equals 280, with S1 equals 24, X3 equals 8, X1 equals 2, S4 equals 5, and S2, S3, and X2 equal to 0. Now solving Z in row 0 yields Z equals 280 minus 5X2 minus 10S2 minus 10S3. We can see that increasing X2, S3, X2, S2, or S3 while holding the other non-basic variables to 0 will now cause the value of Z to decrease. The solution at the end of iteration 2 is therefore optimal. What is the optimality rule? A canonical form is optimal for a maximization problem if each non-basic variable has a non-negative coefficient in the canonical form row 0. So, so the idea, again, if you look at this last Tableau, you look at row 0. Now, how do we know if we found an optimal solution? We have to look at row 0. So this is row 0. And for a maximization problem, if you look at those coefficients and there's no negative values there, then that means that you have found an optimal solution. If you find a negative value in row 0 after completing the iteration, that means that you still have to do another iteration to enter that negative coefficient. But at this point, there's no negative coefficient in row 0, so that means we have found the optimal solution. The optimal solution is Z equals 280 with X1 equals 2, X3 equals 8. So in summary, solving the example LP using the Simplex Tableau method. So we have this problem, right? We started with this problem. We put the problem into standard form. And then we set up our initial Tableau. We found that basic variables for the initial solution. And so in the initial Tableau, I always like to keep track of my basic variables. So my basic variables in that initial Tableau. So these are my basic variables: Z, S1, S2, S3, and S4. So we look at this initial Tableau. This is my initial solution right here. And from here, I can look at the row 0 to see if there's a negative coefficient in row 0. So I look at row 0 here. Is there any negative coefficient here? Yes. We have 3 negative coefficients, minus 60, minus 30, and minus 20. So which one? I'll choose the one that is the maximum negative coefficient, or the highest negative coefficient, or the largest negative coefficient. So in that case, that will be minus 60. So that tells me that X1 is going to enter. Now I need to perform the minimum ratio test to identify which decision variable is going to leave. So the minimum ratio test is performed by looking at these coefficients and the right-hand side. So I'm going to divide 48 divided by 8, and that is equal to 6. I divide 20 by 4, and that is equal to 5. And then I divide 8 by 2, and that is equal to 4. If I try to divide 5 by 0, that's undefined. So we don't do that. And by looking at this minimum ratio test, I identify this as the minimum. So that means that S3 is going to leave. Okay, so you're leaving. On the second Tableau, I already made these basic variables, so I'm not showing the elementary row operations. So X1 is now part of the solution. So these are my basic variables. This is Z, this is S1, this is S2, X1, and S4. Again, at this point, I'm done with the first iteration. So I look at the row 0 and see if there's any negative coefficient. The answer is yes. There's a negative coefficient here, so that means that X3 is going to enter. I need to identify who's going to leave by doing the minimum ratio test. 8 is the minimum, so that means that S2 is going to leave. So on the next iteration, X3 is going to enter, S2 is going to leave. So these are my basic variables: Z, S1, X3, X1, and S4. At this point, I check if I have any negative coefficient here. The answer is no, so I'm done. That's the optimal solution. So the optimal solution is S1 equals 24, right? So S1 equals 24, X3 equals 8, so X3 equals 8, X1 equals 2, and S4 equals 5. So that's the optimal solution. X1 equals 2, X2 equals 0, and X3 equals 8. The simplex method can be used to solve minimization problems in two different ways. Okay, so the problem that we just solved is a maximization problem, but we can also use the simplex method to solve minimization problems. Method 1, so we can do two things. For method 1, the optimal solution is the point x1, x2 that makes z equals 2x1 minus 3x2 the smallest. Equivalently, this point makes a maximization of minus z equals minus 2x1 plus 3x2 the largest. This means that we can find optimal solution to the LP by solving the following LP. So we can transform the objective function from minimization to a maximization by multiplying by -1 on both sides. And then solve the problem as we just did for a maximization problem. So in summary, multiply the objective function for the minimum problem by -1 and solve the problem as a maximization problem with the objective function minus z. The optimal solution to the maximization problem will give you the optimal solution to the minimization problem. As a note, the optimal z value for the minimization problem is going to be equal to the minus optimal z value for the maximization problem. For example, solve the LP shown to the right using the simplex Tableau method. So we have a minimization problem and two constraints. For method 1, solving the modified LP uses minus z as the basic variable in row 0. After adding the slack variables S1 and S2 to the constraint, we obtain the initial tableau. Okay, so I'm not going to show the whole thing. Well, let me do that. So at this point, we have basic variables minus z, S1, and S2. Okay, so this is the initial solution. We have S1 and S2. S1 equals 4, S2 equals 6. We have a negative coefficient here. So this is a maximization problem. We look for the largest negative coefficient. So that means that X2 is entering. And we do the minimum ratio test. And we get that S1 is leaving. So on the next iteration, we have the following basic variables. After performing the Gauss-Jordan elementary row operations, we have the following. We have minus z. We have what is x2 is entering, so x2 and s2. So at this point, we look at the row 0. There's no negative coefficients here, so that means that we have found the optimal solution, which is minus z equals 12 with x2 equals 4 and s2 equals 10. So at this point, we have found the optimal solution for the maximization problem. So in order to get the optimal solution for the minimization problem, we take this minus z equals to 12, and we multiply this by -1 on both sides. So that will be equal to z equals -12, which is what we have here. The second method, a simple modification of the simplex algorithm, can be used to solve minimization problems directly. Modify step 3 of the simplex algorithm as follows. If all known basic variables in row 0 have non-positive coefficients, the current basic feasible solution is optimal. If any non-basic variable has a positive coefficient, choose the variable with the most positive coefficient in row 0 as the entering variable. This modification of the simplex algorithm works because increasing a non-basic variable with a positive coefficient in row 0 will decrease the z. So with the modification now, instead of looking for the largest negative coefficient, we are looking for the largest positive coefficient. So my basic variables now are Z, S1, and S2. This is my initial solution with S1 and S2 equals 6 and S1 equals 4. So I look for the largest positive coefficient in row 0, and that will be +3. So I know X2 is entering. So I need to do the minimum ratio test. So I do 4 divided by 1, which is equal to 4. And then I do 6 divided by -1, which is negative. So we don't take that into account. So S1 is leaving, X2 is entering. So what we have here is the basic variable, Z. X2, S2. And then we solve. We do the elementary row operations to make this 0, 1, 0. And after completing the iteration, we look for a larger positive coefficient here for the non-basics. And the non-basics are -3 and 0, so there's no positive coefficient. So that means that we are done. And we got the same solution. Z equals -12, X1 equals 0, and X2 equals 4. For some LPs, more than one extreme point is optimal. If an LP has more than one optimal solution, it has multiple optimal solutions. If there's no non-basic variable with a 0 coefficient in row 0 of the optimal tableau, the LP has a unique optimal solution. If there's a non-basic variable with 0 coefficient in row 0 of the optimal tableau, it is possible that the linear programming may have alternative optimal solutions. So here's an example. Solve the following LP using the Simplex Tableau method. So here we have, so now I'm gonna go and show you the last Tableau. So after performing the iterations, we got to this solution. Z equals 12, X1 equals 6, X2 equals 2. Our alternative optimal solution could be also this one. And the difference here is that we have, for the basic variables, you see that the sets are different. In one, we enter X1, in the other one, we enter X2. But we still get the same solution. And that happens here after iteration 1. And in this problem, we are maximizing, right? So after we complete the iteration, we see that there's no negative coefficients here, right? However, we notice that there's a non-basic variable with a 0 coefficient. So that could tell us that there might be an additional solution or multiple solutions, multiple optimal solution for this problem. So what we did here is like, we found a 0 in row 0 for a non-basic variable. So let's enter that one. And after entering that into the solution, we found that we still get the same objective function value of 12 with a different x value, which is x2 equals 6. For some LPs, there exist points in the feasible region for which Z assumes arbitrarily large or arbitrarily small values. When this occurs, we say the LP is unbound. An unbound LP occurs in a maximization problem if there's a non-basic variable with a negative coefficient in row 0 and no constraint that limits how large we can make this non-basic variable. Specifically, an unbound LP for a maximization problem occurs when a variable with a negative coefficient in row 0 has a non-positive coefficient in each constraint. So the ratio test fails. So if we look at this example, X2 is going to enter So we perform the minimal ratio test so that means that S2 is leaving. And after performing the first iteration, we found that we still have a negative coefficient here. So X1 is gonna enter. In iteration 2, we find that S2 is negative. So negative 3 for X2, so S2 can enter. Well, but when we perform the minimum ratio test, the coefficients for the columns are both negative, so the minimum ratio test will fail because we cannot have a minimum ratio that is negative. So what that means is we would like S2 to enter the basis, but there's no row in which S2 has a positive coefficient. Therefore, the LP is unbound. Okay, so that concludes our discussion of the simplex algorithm in this lecture.